Hello and welcome back to Physics and Maths Tidbits. In this video I will be deriving the fluid equation in cosmology from a non-general relativity standpoint using thermodynamics. Additionally, I will then solve the fluid equation for a general equation of state, and then we will explore some consequences. So to begin, we can start from the first law of thermodynamics. du is equal to TdS minus PdV. Now, to make this equation applicable for cosmological purposes, we need to ensure that it adheres to the cosmological principle, which, as a reminder, is that the universe is homogeneous and isotropic. So in this case, we're going to take V to be the size of the universe as a whole, and we're also going to set ds equal to 0. The reason why we're not allowing any change in entropy is because that would mean that there would be an energy flow in the universe, which would lead to a violation of the cosmological principle. So we have du is equal to minus PdV. For a substance with energy density U, we have U is equal to rho c squared, where rho is the equivalent mass density. Additionally, we have that big U, our thermodynamic U, is equal to the energy density times the volume, i.e. the energy is the energy density times the volume, which makes complete sense. From these guys here, we can take the infinitesimal du, but to do that first, we will substitute in our energy density U is equal to rho c squared, which gives us big U is equal to rho c squared V. And therefore, taking the infinitesimal and applying the chain rule, or the product rule, sorry, we can have c squared rho dV plus V d rho. We may now equate this with our cosmologically considered version of the first law of thermodynamics. And this gives us c squared rho dV plus v d rho is equal to minus p dV. Taking everything over to the left hand side and factorizing out or expanding out the c squared term, we get c squared rho dV plus c squared v d rho plus p dV is equal to 0. We may then divide through by c squared and then subsequently factorize out our infinitesimally, our volume components. So that would be rho plus p over c squared dV plus v d rho is equal to 0. Additionally, we may also divide through by v, which gives us rho plus p over c squared dV by v plus d rho is equal to 0. Similarly, we may now introduce a time dependence by dividing through by the infinitesimal dt. It should be noted as well that most of these actions are crimes in mathematics, but because we're physicists, we can do what we want. And an alternative notation for this is rho plus p over c squared v dot over v plus rho dot is equal to 0. And this is nearly the form of the fluid equation. However, we note that in cosmology, we know that the volume will scale as a cubed, a being the scale factor of the universe. So we have v dot over v is equal to 3 a dot over a, and a dot over a is just equal to the cosmological parameter h, or the expansion parameter, sorry, the Hubble parameter. Sure, it's the Hubble parameter. Finally, substituting this in, we get the fluid equation rho dot plus 3h rho plus p over c squared is equal to 0. This equation will tell us how density of different constituents of the universe changes as the universe expands. To solve this equation, we need an equation of state for the fluid of the universe. And for this video, we will choose P is equal to W rho c squared, where W is a constant, the equation of state parameter. Rearranging the fluid equation to have d rho by dt on one side, we have d rho by dt is equal to minus 3, and substituting a dot over a back in for h, a dot over a rho plus p over c squared. We can also write this out slightly more explicitly as 1 over a dA by dt rho plus p over c squared, as this will make it slightly easier in the future when we solve this equation by separation of variables. We can also now substitute in our equation of state for p, which gets us minus 3 1 over a dA by dt rho plus w rho. We can then factorize out the rho's to get minus 3 1 plus w rho 1 over a dA by dt, which now leaves us in a position where we can comfortably solve this by separation of variables. taking all components of rho to the left-hand side and all components of A and T to the right-hand side, we have 1 over minus 3, 1 plus W. The integral of 1 over rho d rho is equal to the integral of 1 over A dA by dt dt. Just to make this really explicit, you can see I've moved these parts over here and these remain on this side. And then we integrate over the infinitesimals. The integral of 1 over x is ln x, which gives us our solution. 1 over minus 3, 1 plus W, ln rho is equal to, and on this side we will do some more mathematical crimes and cancel out the dt's, so we have 1 over A dA, which is ln A, plus some integrating constant c. Using the rules of logs, we can move this guy to the row, and we will also bring both logs over to one side. So we have ln rho to the minus 1 over 3, 1 plus W, minus ln A is equal to some constant c. The difference between two logs is the log of the fraction of the bits inside the brackets. So we can say that ln rho to the minus 1 over 3, 1 plus W divided by A is equal to some constant c. We may then raise e to the left hand side and right hand side to cancel out the log, which gives us 1 over A rho to the 1 over minus 3, 1 plus W is equal to e to the c, which is just equal to some constant c primed. We can then move A over onto the right hand side, and we have rho to the 1 over minus 3, 1 plus W is equal to A c primed. And then finally, taking the inverse of the power on rho to the right hand side, we have rho is equal to AC primed to the minus 3, 1 plus W. C primed to the minus 3, 1 plus W is just a constant, which we will set equal to rho naught, and A to the minus 3, 1 plus W is the factor left. And this gives us our solution to the fluid equation for an equation of state P is equal to W rho C squared. This solution tells us how the density of a certain type of constituent in the universe changes as the universe expands with A. So some examples of this are W is equal to 0, which is matter. This includes dust, baryons, and classical objects where the kinetic energy is way below the rest mass energy. And in this case, we have rho is equal to rho naught, A to the minus 3, which gives us the same dependence as you would have found previously, where the matter density in the universe is proportional to A to the minus 3, which is a very standard result in cosmology. Additionally, we may take W is equal to a third for radiation, such as photons and relativistic matter, and in this case we have rho is equal to rho naught, A to the minus 4, which again is a very standard result in cosmology. So just to recap, we have derived the fluid equation in cosmology using non-relativistic principles from thermodynamics, and then solved the equation for a particular equation of state and looked at some of the consequences of how that affects matter and radiation as the universe expands. Though the derivation in this video is not particularly complicated, there are many steps of algebra which are commonly left out of course notes. I hope you have learned something from this video.